Hello. We're going to start this time picking up exactly where we left off last time. Okay, so remember we were doing synthetic division, and we said that if when you do your synthetic division, if your remainder is zero, right, that means you have a factor, right, a solution, a root, and then you can find a corresponding factor, I guess I should say. And so that's actually our factor theorem that says for any polynomial, okay, x minus k is a factor of the polynomial if and only if f of k equals 0. Okay, so notice that we have these polynomials now. Look at fourth degree, a fifth degree. You know, we said factoring is really, really important, but I don't know how to factor this thing. I might try grouping, right? But I notice that it doesn't factor by grouping, and this, oh my goodness, you know. But now we're going to have a method to factor these things. And if I can factor them, I can find my zeros. So, doing synthetic division, don't forget to double check your exponents. This one goes 4 to 2, so I'm going to have to put a placeholder in there. Okay, so 2, 0, 3, negative 5, 7. And it says it's just asking us if x minus 1 is a factor of each polynomial. Well, if x minus 1 is a factor, that must mean that 1 would be a 0. So don't forget, if it gives us the factor, we got to change the sign. If it gives us the k as the 0, they've already changed the sign for us. Bring down the 2 to get us started. 1 times 2 is 2. Add them together. 1 times 2 is 2. Add them together. 1 times 5 is 5. Add them together. 1 times 0 is 0. So since that is not 0, this one is not a fact. This one does not have x minus 1 as a factor. Let's check this one. 5, 4, 3, 2, 1, 0. I'm good with all my exponents, so I'm just going to put these coefficients into my division frame, and once again try 1, only because that's what it's asking me, right? So bring the 3 down to get us started. 1 times 3 is 3. Add them together. 1 times 1 is 1. Add them together. 1 times 2 is 2. Add them together. 1 times negative 6 is negative 6. Add them together. 1 times negative 1 is negative 1. Yes, this one has a factor of x minus 1. Okay, so what's important for that, where we're going is then, if this is a 0, then I know that I have a factor of x minus 1, and that means this, remember it's going to be 1 degree less, so the other factor is 3x to the 4th plus x cubed plus 2x squared minus 6x minus 1. And notice I have now this one didn't ask me to, but that's what we're about to do. I have factored this 5th degree polynomial into 2 factors, and then I could continue to do the same with this one. Okay, so that's our goal. All right, this one says to factor this polynomial, excuse me, if we know that negative 3 is a 0. This time it didn't give us the factor, it's given us the actual 0, so we don't change the sign. So 3, 2, 1, 0. I don't have any missing terms. So if negative 3 is a 0, I better get a 0 over here. So bring 6 down. Negative 3 times 6 is negative 18. Okay, add them together. Negative 3 times 1 is negative 3. Add them together. Negative 3 times negative 1 is positive 3. Yes. So that means so far I have factored this thing to x plus 3, right? If this is the 0, that means x equals negative 3. So if I added 3 to both sides, I'd have the factor x plus 3, right? Okay, and because this was a cubic, this is going to be a square. So I've got 6x squared plus x minus 1. Okay, and now, since this is a quadratic, right, we can factor our quadratics. So I just need, let me go over to the side since I'm not going to get my shortcut here and find those two factors. I just need two numbers that multiply and give negative 6 and at the same time give 1. So that's going to be positive 3, negative 2. Right, now I can factor by grouping. So I can factor out a 3x, and that leaves 2x plus 1. I can factor out a negative 1, which leaves 2x plus 1. Now the 2x plus 1 can factor out and leave 3x minus 1. Okay, so then we have all of our factors. We have the x plus 3, and now I know that this is 2x plus 1 times 3x minus 1. And now, because of this synthetic division in our factor theorem, we're able to factor a polynomial that previously I wouldn't be able to factor. All right, so here's our rational zeros theorem. Sometimes, and I'm used to calling it the rational root theorem. So once we find zeros, you can either call them zeros, you can call them roots, you can call them solutions, and in the next section when we're graphing these functions, we'll call them x-intercepts, right? Those are just different terms for the same thing. So if p over q is a rational number written in lowest terms, so if you have some number, and remember a rational number, that's also a rational number. So whole numbers are also rational numbers. So we're not saying they have to be a fraction, but it could be. Okay, if it's a zero of the polynomial, right, with integer coefficients, notice that, so at least we're always going to have integer coefficients, then p has to be a factor of the constant term, and q has to be a factor of the leading coefficient. Okay, so what does that mean? It means that, okay, if we didn't have this factor theorem, and I wanted to try to factor this thing like we were before, and that problem, the previous problems we've had so far in this section, they gave us one of the factors, right, or one of the zeros. But here, you know, we're not, when we actually have a problem, we're not going to be given some of the zeros, you know, if we're trying to solve something whenever we get into our field or whatever we need to be doing. And what are you going to do? Just guess forever what, and divide this by what, 1, 2, 3, 4, 5, and then when are you going to try negative 1, negative 2, and then what if all your solutions are fractions? How long would it take you to try to divide 2/3 into this, or 3/5? So this rational zero theorem gives us some help with, it tells us, hey, if this has some zeros, it's going to be one of these if they're rational. Now, it won't get complex ones, and it won't get radical solutions. But if it's a rational number, this will tell us what it is. So all we have to do is p has to be a factor of the constant term. So it's either plus or minus 1 or plus or minus 2. The only factors of 2 are 2 times 1, but they can be positive or negative, right? Then q has to be a factor. Let's change that just for emphasis. So q has to be a factor of the leading coefficient. So q is, so you think of all the factors of 6, you know, 1 goes into 6, 2 does, 3 does, 4 doesn't, 5 doesn't, but 6 does, right? All the factors of 6. So what that means is P over Q are possible solutions or possible zeros to this has to be all of these numbers divided by all of these numbers. So it's either, okay, 1 over 1, 1 over 2, 1 over 3, 1 over 6, or 2 over 1, 2 over 2, I already have 1 listed, 2/3, or 2/6, which is 1/3, which I already have listed. So here's the only things that's possible to be zeros of this solution. Other than there could be complex and radical ones, right? But so after I tried 1 and 2, there's no need to try 3, right? Then I would try -1 and -2. And then I could try 1/2 and 1/3 and 1/6. Okay, so the rational root theorem, rational zero theorem, is going to be really important for us. Okay, so here we are, and it just tells us to find the zeros and factor. Excuse me, let me get a drink. So pay attention to the question, whether it's asking you to factor it or find the zeros. I think on all these examples on here, I'm doing both just so that we can, see how the difference between them and get practice on doing both. But pay attention to what your homework wants, or when you do an exam, which one the exam is asking for. Okay, so first of all, I'm going to see if I can factor these things by grouping, because if I can factor them by grouping, that's way easier. But this thing, I can tell I can't factor it. So I'm going to try to figure out, well, what would my possible zeros be? Okay, so P would be, is this the same one we just did, that we just had our factors from? I think so. We should have just kept those, but okay. P would be factors of 2, which are only 1 and 2. Okay. Q, factors of 6, which are 1, 2, 3, and 6. So P over Q, the only ones we have to try would be 1, okay, and then 1/2, and 1/3, 1/6, 2, 1 we already have listed, like we mentioned before, and 2/3, because we already have 2/6, which is 1/3 listed. Okay. So now I'm just going to start dividing by these things and see if I can find a zero. Okay, 4, 3, 2, 1, 0. I don't have to worry about that. 6, 7, -12, -3, 2. Let's just try 1. Okay, 6 times 1. So it's also important here, you might see, that we don't want to make a mistake here and miss one of our zeros, right? So 7 and 6 is 13. 1 times 13. 1 times 1 is 1. -3 plus 1 is -2. Woohoo! We already found one of our zeros. So I know that x equals 1 is a 0. And not only that, that means this is 6x cubed plus 13x squared plus x minus 2. Okay, So I'm going to stop here and try to factor it by grouping, but I notice I can't. So I'm just going to continue with my synthetic division. Now, I got to be careful, and I have to check 1 again, because remember, sometimes we get multiple roots that's the same number, right? So I've got to check 1 again. 6, 13, 1, -2. And let's try 1. 1 times 6 is 6. 13 plus 6 is 19. And I can tell that's not going anywhere, right? It's not going to be 0. I don't really care what it is if it's not 0. All right. So then I'm going to move over and try -1. Okay. So I've got -6. So then I've got -7. I can also tell that this isn't going to 0. All right, so I've used up my 1s. I'm going to move over and do 2. Just to avoid those fractions as long as I can, right? Okay, so 2 times 6 is 12. Add them together. It looks like -2 is going to be a good option, right? Because then I'd be subtracting here. But let's go ahead. 25. Yeah, this is not going to 0, right? Not going to be 0. So let's try -2. Just don't miss your root. Be careful. -2 times 6 is -12. This is looking better. -2 times 1 is -2. And so -2 times -1 is +2. Yes, I just found another 0. And that means this is a quadratic equation now. This was a cubic, so this will be a quadratic, which means, hey, it's 6x squared plus x minus 1. Okay, and I can factor that. So I'm going to go over to the side and do that. I need 2 numbers that multiply to give -6 and add to give 1. So once again, I think we just did this. 6x squared plus 3x minus 2x minus 1. And then factor it by grouping. So we have 3x times 2x plus 1. And then factoring out a -1 gives us 2x plus 1. Factor out that 2x plus 1, and we have 3x minus 1, which means I can get my other 2 zeros, right? If we set this equal to 0, right, then 2x plus 1 would give me that x equals -1/2. And if I set this one equal to 0, x would be 1/3. Notice those numbers are listed up here in our possible solutions, right? Our possible zeros. So there's the zeros, but it also asked me to factor it. So here's 2 of the factors, and then the other 2 I can get from this. If x equals 1 is a 0, then I have x minus 1 as a corresponding factor, x plus 2 for this corresponding factor, and then of course, now notice if we'd had a 0 and we didn't already have these factors down here, our factor is not x plus 1/2, right? The factor is not x plus 1/2. But we could easily find what the factor is if I can't visually just see that by making this equal 0. So I'd multiply both sides by 2, right? So then you would have 2x equals -1. Add 1 to both sides. 2x plus 1 equals 0. And we'd say, oh, okay, so here's our factor. Of course, we already have it from over here, but if all of these were fractions, right, that's how we would find our factors. So then we have 2x plus 1, and finally 3x minus 1. So here it is factored, and then here's my zeros. Okay. Okay. So we have the fundamental theorem of algebra, which tells us that any polynomial function of degree 1 or more has at least one zero. Okay, that's the fundamental theorem of algebra. And it turns out that any polynomial of degree n has at most n distinct zeros. So I like to change this to saying has n zeros. Okay, so if we have a fifth degree polynomial, it's going to have 5 zeros. We already talked about this when we did quadratics, and we said we'll always get 2 answers. Now, sometimes they might be the same number, so that's why this is saying at most n distinct, but it will have n zeros. So that's another thing that's going to help me look at some of these solutions. I better get, if I've got a 6th degree polynomial, I better get 6 zeros. And another theorem tells us that if one of the zeros is a complex number, then its complex conjugate is also a zero. So if we get one complex zero, then I have 2 because I know the conjugate is also a zero. Whoops. Okay, so in addition to that, we have Descartes' rule of signs. Okay, so some of you may have heard of Rene Descartes before. He's a famous mathematician. You also, if you take some philosophy classes or something, you may hear about him. But we can read this. It's pretty crazy and hard to understand unless someone tells you what it is. It's saying the number of positive zeros either equals the number of variations in sign occurring in the coefficients of the function, or is less than a number of variations by a positive even integer. And we can do the same thing with the negatives. And so you might be saying, oh, what does that mean? Okay, well, it's not too bad. So let's look at an example that you have to, once you're shown, it's not too bad. And this Descartes' rule of signs, it's really easy to check, and it's going to help me sometimes cut my work in half, right? You notice from that problem that we did earlier, what we have to do? 1, 2, 3, what did we do? About 4 synthetic divisions, and that was just for a 4th degree. Okay, so sometimes, we might have 8 or 9 synthetic divisions just trying to solve one problem. And so Descartes' rule of signs can help me cut my work in half. All right. So this says, consider the polynomial function, find all rational zeros and factor f. So a couple of things I know from those theorems we just had. I better have 4 zeros, right? Because it's a 4th degree polynomial. I will have 4 zeros. Now they may not be 4 different zeros, but I'll have 4 zeros. So what Descartes' rule of sign is, let's do it first. And the first time that I use it, it's going to seem long and complicated, but then, we can shorten it out. It's just going to seem long because I'm explaining it. So it said, to determine how many positive solutions there are, count the number of sign changes if x is positive, which is your original function, right? So it goes from a plus to a plus, so it doesn't change. Oh, here's a sign change. It goes from a positive to a negative. Then it goes back to a positive, and then it goes back to a negative. So this changes signs 3 times. Okay, now the crazy thing about Descartes' rule is that you go down by 2 every time until you get to 1 or 0. So this is going to have 3 or 1 positive solutions. I'm going to actually write it up here so at the end when we get our answers we can check. So there's 3 or 1 positive solutions. Okay, Now, what we do is we count the number of sign changes for f of negative x. So I would have to plug a negative x in everywhere, which would mean negative x to the fourth plus 2 times negative x cubed minus 3 times negative x squared plus 24 times negative x minus 180. So simplifying this, 4 negatives, 3 negatives, 2 negatives plus this one stays negative, 1 negative, and then that's negative. So count the number of sign changes. It goes from a positive to a negative, and then doesn't change, doesn't change, doesn't change. So there will be one negative solution. Okay, now you might be saying, wow, no, that's a lot of trouble, but I could just imagine plugging in a negative. This is literally what we would be doing, but I can think, oh, if I put a negative in there, it's going to be positive. If I put a negative in here, it's going to be negative. If I put a negative in here, it's going to stay negative, negative, right? So I could just do it that quickly. I just wanted to show us literally one time what we were doing. Okay, so 3 or 1, and then 1. Okay, so there's 3 or 1 positive and 1 negative, just to keep track for us. Okay, but so really I don't need to keep track of that now because it didn't help me. The only time Descartes' rule of sign helps me is if one of these is 0. And then it's like, oh, there's not any negative solutions. I don't have to try any of the negatives. Okay, once I try 1, I can move to 2. I don't have to do negative 1. Or if it said there's not any positives. So that's what I'm looking for. I'm looking for that help. Okay, so let's start. Let's see what our possible solutions are. Oh, my goodness. P is factors of 180. All right, so 1, 2, 3, 4 doesn't, and I'm just, I can look at just 18 basically and tell if the number goes into it. So 4 doesn't, 5 doesn't, but 6 does. At this point, I might just stop. If I don't have my solution by the time I try all of these, then I can go back and see, well, what's my next number to try? But hopefully the book's going to be kind of nice to us and not have to go too far. So now Q was only 1, so if I divide all those by 1, really that is my possible solutions. Right? Okay. So let's put one more up there just for emphasis sake that we're not done. Okay. Now, 4, 3, 2, 1, 0. I don't have any missing terms. 1, 2, negative 3, 24, negative 180. I didn't get any help from Descartes, so I'm just going to go down my list and try 1. Okay, 1 times 1 is 1. Add them together. 1 times 3 is 3. Add them together. 1 times 0. Add them together. It's not 1, right? That's not going to be 0. So I'm going to try negative 1. Thanks to Descartes, right? I don't get any help. Okay, negative 1 times 1 is negative 1. Negative 1 times 1 is negative 1. Negative 1 times negative 4 is positive 4. So it's not negative 1. All right, used up my 1s. Let's try 2. And you can see how it's nice when you get help from Descartes, right? 2 times 1 is 2. Add them together. 2 times 4 is 8. Add them together. 5 times 2 is 10. Add them together. And 2 times 34 is not 180, so since it's not 180, whatever else it is, I don't care, right? 68. So let's try -2. -2 times 1 is -2. -2 times 0. -2 times -3 is 6. Okay, -2 times 30, -60. So it's not 2. We're getting closer to it though, so maybe it'll be 3. Let's hope, right? Okay. So let me see what I'm doing. Okay. All right, let's try 3. Okay, 3 times 1, whoops. 3 times 1 is 3. Add them together. 3 times 5 is 15. Add them together. 3 times 12 is 36. Add them together. Oh, 3 times 60 is 180. Woohoo! See how awesome it is when you actually find one? Then you get so excited, right? Okay, so I have found one of my zeros. And don't forget, at this point, I'm always going to stop and try to factor that thing because it might save me a bunch more work. Don't forget that. After every juncture, try to factor it. Okay, plus 5x squared. Oh, and look at this. It's a good thing that we tried this. Okay, because I think I can factor out an x squared here, and it leaves x plus 5. And then I can factor out a and then I can factor out a 12, and that leaves x plus 5. Awesome, awesome, awesome. Now I can factor out the x plus 5, and I'm left with x squared plus 12. So notice I was not going to find, I even missed my 5 up there. I was not going to find another factor on my synthetic division until I got to 5, right, -5 actually. So it's really important to stop and try to factor at every juncture. So now it says find all rational zeros and factor it. This doesn't factor any further as far as a factor goes, right? So my factors of this are my corresponding factor with the 0 of x equals 3 is x minus 3. And then I have x plus 5 and x squared plus 12. All right, so there it's factored. Now to list my zeros, I have x equals 3 and x equals -5 from this factor, but we're going to have to set this equal to 0 and solve it for those zeros. So if I subtract 12 from both sides, and then I do the square root method, so I'll have x equals, don't forget your plus or minus. If you've got an I under a radical, that has to come out as an I. If you've got a negative under a radical, that has to come out as an I. And then you got to simplify that radical. So we're going to change that 12 to 4 times 3, right? Because you can do the square root of 4. So you can bring that out as plus or minus 2, the square root of 4. But then that 3 stays in there. So there's your other 2 zeros. And notice we did get 4 of them. All right. And notice it says there's either 3 or 1 positive, and there is 1 negative, right? Now, complex numbers, I know we've got a plus or minus out here, but they're not considered to be positive numbers or negative numbers, right? They're complex. Right? This is really 0 plus 2i squared to 3, 0 minus 2i squared to 3. It's the only reason that plus and minus is in there. It's just 2 separate numbers. They're complex. So there was one positive and exactly one negative. We knew there would be exactly one negative. Okay, let's see. We probably need to try that again, don't you think? Yep, let's try it again. All right, so hey, look, I'm going to get help from Descartes because plus, 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 I know there are no positive solutions. So I don't have to check any of the positives. Okay, so let's see what our P's and Q's are. So P, factors of 6. So 1, 2, up. 1, 2, 3, 6. Q, factors of 4. 1, 2, and 4. That means my P over Q's, what's possible, is all of these numbers divided by all of those numbers. So if I divide them all by 1, it's possibly 1, 2. That's exactly what I did last time. I don't know what that is. Okay, 1, 2, 3, 6. Then divide everything by 2. So we get 1/2. 2 divided by 2 is 1. It's already listed there. 3/2. 6/2 is 3. I already have that listed. So 1/4. 2/4 is already listed. 3/4. And 6/4 is 3/2. So it's already listed. Okay. And I don't have to try any of the positives. So 3, 2, 1. Oh, first, don't forget, I did think about if I could factor this. But, 4x plus 3, that'll be, if I factored a 2 out over here, it'd be 4x plus 3. Let's just see if we can factor it right off the bat. Can factor out an x squared, and that leaves 4x plus 3. Can factor out a 2, and that leaves 4x plus 3. See how much easier it is if you think about factoring them first? Okay, so it asks us to factor it and find the zeros. So there it is factored. Okay, so if I was going to find the zeros, then I just set each of these equal to 0. So x equals negative 3/4. And then x squared plus 2 must also equal 0. So x squared has to equal negative 2. Okay, square root both sides. So x is plus or minus I square roots of 2. Yes, there were no positive solutions. And I did get 3 separate solutions. Here's 2. Notice how when they're complex, you always have the conjugate there. Okay, so there's my solutions. All right. All right. Let's try that again. All right. So this one won't factor, right? Let's see if we can get some help from Descartes. I see that it's changing signs, so there's some number of positive solutions, possibly. You know, it changes signs 2 times, 1, 2, no, it changes signs, yeah, 4 times. It changes 1, 2, 3, 4. So really there could be, if you subtract 2, there could be 4 or 2 or 0. So there might not be any positives, but that's a pretty big gamble. Might not be. There also might be 4. But let's imagine plugging a negative in then. If I plugged a negative in, that's still going to be positive. Okay? If I plug a negative in here, that's a negative negative, so this one would be positive. If I plug a negative in here, it would be positive, so it's going to stay positive. Hey, look at this. If I plug a negative in here, a negative negative would be positive. So there's no negative solutions. That's what I'm looking for. That's the help from Descartes that I want. Okay, so let's find our P's and Q's. Okay, P is factors of 16. So 1, 2, 4, 8, and 16. P's are factors of 1. So if I divide all those by 1, that just stays the same. Okay, so now we're just going to start our dividing. 4, 3, 2, 1, 0. I don't have any missing terms. Don't forget to always check that. That messes a lot of people up. All right, and I'm going to start with 1. So 1 times 1 is 1. 1 times negative 7 is negative 7. What's that, 17? And 1 times 17 is 17. Oh, that was close. So what's that, negative 15? Not 0. It's so close though, I'm going to double check my math. 1, so that is negative 7. Negative 7, that is 17. And that's 15. Okay, so it's not 1. And I don't have to check negative 1, right? Because Descartes helped us out this time. So let's move to 2. 2 times 1 is 2. 2 times negative 6 is negative 12. 2 times 12 is 24. Hey, hey, hey. 2 times negative 8 is negative 16. Woo-hoo-hoo. So we found one of them. It's exciting when you find one, isn't it? Okay, and then let's check this. This will be a third degree. So let's check it and see if it'll factor. X cubed minus 6x squared plus 12x minus 8. I can factor an x squared out here and leave x minus 6, but over here I can factor a 4 out and it does not leave x minus 6, right? So doesn't factor. That's all right. We can find them with synthetic division, right? All right, so let's just go again. Now, don't forget, I've got to recheck that 2, because 2 of my solutions might be 2. Okay, 2 times 1 is 2. 2 times negative 4 is negative 8. Hey, hey, hey. Oh, it's a good thing I double checked that too. I don't want to miss one. And then that makes this x squared minus 4x plus 4. And hey, if we're good at factoring, this is a perfect square trinomial. This is x minus 2 all squared. Hey, which means all 4 of my solutions are 2. It's a good thing we didn't move on to 4. We would have never found another solution, right? So you got to remember to check those solutions until they don't work anymore, right? Then move to the next one. So here's my zeros, and when I'm writing my answer, I don't have to write that 2 4 different times. Okay, and here's my factors too. It is x minus 2 to the 4th power. Because there's 4 of them. Okay, cool. Let's see what we got now. All right, another one. Let's try it again. All right, so signs are changing, so no help from Descartes on that, but let's see if we plug in a negative. This would stay negative. This would be a positive, so stay negative. This would be negative. This would be negative. This would, good, we got some help again. Okay, so we know there are no need to check the negative possible solutions. So let's look at P's and Q's. P is factors of 16 again. So 1, 2, 4, 8, and 16. Since Q is 1, when I divide them by 1, it stays. So that's my P over Q's for this one. 5, 4, 3, 2, 1. No terms are missing. So we've got 1, negative 6, 14, negative 20, 24, negative 16. All right, let's just try 1. 1 times 1 is 1. 1 times negative 5. 1 times 9. 1 times negative 11. And 1 times 13 isn't 16, so it's not 1. We don't have to try negative 1, thanks to Descartes. So let's try 2. 2 times 1 is 2. 2 times negative 4. 2 times 6 is 12. 2 times negative 8 is negative 16. This is looking good. 8 times 2 is 16. Woohoo! We found 1. It's 2 again. Interesting. I wonder if all 5 of them are going to be 2 again. All right. Now this is a 4th degree polynomial, so I can tell from right here I can't factor that. I'm just going to, if you need to rewrite it and look at that, that's fine, but once you get used to what you're looking for, you can tell without putting it back into those variable terms. All right, and what do we try? Right, 2 again. 2 again, don't forget. 2 times 1. 2 times negative 2. 2 times 2. Hey, if this is all 5 of them too, I'm going to be a little, negative 4, negative 8. So another one is 2. All right, and hey, I can tell by looking at that will probably factor, because you can factor a 2 out here, right? So let's put it back in. If this was a 5th degree, right, that's a 4th degree, so that's a 3rd degree. X cubed minus 2x squared plus 2x minus 4, and let's factor it by grouping. So we can factor an x squared out, which makes x minus 2. There's another one that's 2, but the last isn't, at least. And then we can factor a 2 out, and that leaves x minus 2. So there's the x minus 2, and then x squared plus 2. All right, so if we're factoring this thing, here's our factors, right? Here's these 2. Plus I have 2 more factors. It's going to be x minus 2. So there's really going to be 3 of these, right? That's what it looks like when it's factored. Does that make sense? Kind of did a little shortcut there. Here's 2 factors of x minus 2, right? And then there was 1 from here. So that's why there's 3, and then this x squared plus 2. All right, so here's 3 of my zeros, and my other 2 are right here. So I need to figure out what that looks like as a 0. Let's set it equal to 0. And then subtract the 2 from both sides, square root, so x is plus or minus I square roots of 2. Okay, so our zeros then are x equals 2 and x equals plus or minus I square roots of 2. All right. And I do have 5 of them. It's just that 3 of them are 2's, right? 3, and then there's 4 or 5, which is a nice thing to double check. Okay, let's see what else we got going on here. Okay, now we're doing kind of the opposite. It's going to give us what the zeros are and ask us to find the function instead of giving us the function and asking us to find the zeros. Okay, so I'm looking for a function. So that's f of x equals, now if it has a 0 and -1, I know it has a corresponding factor of x plus 1, right? If it has a 0 of 2, we've got a corresponding factor of x minus 2. And if it has a 0 of 4, we've got a corresponding factor of x, of x minus 4. So this right here, if I were to multiply this out, this is a polynomial that has these zeros, right? A polynomial. But this asks me to find the polynomial that has these zeros and where f of 1 equals 3. So before I multiply this out, I need to find out what is going to happen. If I if I evaluate that at f of 1, let's see what happens. If I put a 1 in everywhere there's an x, right, then this becomes 2, and this becomes -1, and this becomes 1 minus 4 is -3. So my answer is really 6. F of 1 is 6. I need f of 1 to be 3. What's the relationship between 3 and 6? It's half of it. So what I need to do is I need to put a constant right in here, saying multiply it by a half then. Notice if I had that half right here, right, then it would be right here, and half of 6 is 3, and we'd have our polynomial that we need. So here's the polynomial we're looking for, but I do need to multiply that out, right? I'm not going to take the time to multiply that out for you. Actually, I'm redoing it. I guess I will on one, but on the others, I'm not going to take the time to multiply that out. But here we go, just so that you have an example of that. Just take 2 at a time, right? So x squared minus 2x plus x minus 2, and then that's going to be times x minus 4. So combining those terms so that we can continue to multiply it out. So we would have x cubed minus 4x squared minus x squared plus 4x minus 2x plus 8. Okay, and so then you would combine your terms and distribute the 1/2 for your final function, right? All right. I think let's try that again. Right. Okay. So -2 is a 0 of multiplicity 3. Multiplicity means there's multiple -2's. That's my 0. How many multiples? 3. So that's what multiplicity means, right? It means there's 3 negative 2's. So if I'm trying to find that function again, I know that it looks like this. If negative 2 is a 0, x plus 2 is a factor. And if there's 3 of them, I can write it like that, right? You can write x plus 2, x plus 2, x plus 2. You might have to do that for when you're multiplying it out. But so there's a function. But again, I need the function where if I plug in a negative 1, it equals 4. And if I plug a negative 1 into here, negative 1 plus 2 is 1 cubed. It's just 1. If I need it to be 4, then I need to multiply that by 4, right? So there's my function. The particular function we're looking for. Okay, let's try it again. This time, I'm still looking for a function that has certain zeros, but notice it tells me one of them is 2 plus I. So I have to know, remember our complex theorem. Okay, so if I've got a 0 or 3, that's x minus 3. But if I know that I have a 0 or 2 plus I, the complex conjugate 2 minus I also has to be a 0, right? They only occur in conjugate pairs. So this would be, now look how we're going to write this, x minus 2 plus I. Notice it's the same thing I did to the 3, right? I just made it x minus 3. So x minus 2 plus I and x minus 2 minus I. Okay, so which is x minus 3 times x minus 2 minus I and x minus 2 plus I. Right? I know, you're like, why didn't I just write this? Well, because this is the correct way. It does just happen to turn out to be minus 2 plus I, 2 minus I. But this is the solution that's the 0 that's 2 plus I. Right? I wanted us to see that. And then again, it doesn't give us a specific one, so it just wants any function that those are the solutions, you know. And this it will be our answer then, and I'll multiply it out. Now, just to help us with this, I'll multiply that out for us, just so you can see it. If you don't need to see it, good, all the better. Okay, so it's just doing your distributive property. X times x, x squared. X times negative 2, negative 2x. X times I, so xi, and then move to the next one. Negative 2x, negative 2 times negative 2, positive 4, negative 2i. Okay, and then move to the next one. Negative ix, positive 2i, and negative I squared. Now, notice we have plus xi minus xi. Okay, minus 2i plus 2i. And don't forget, anytime you have an I squared, that's negative 1. So then this term would be x squared minus 4x, and then here's a positive 4, and here's a negative 1, so 4 plus 1, 5, and then continue. Okay, I think that's our last example. Let's double check, see if this goes anywhere. Oh, no, we have another one. Let's see how many. This is the last one. So let's just try that again. Okay. Oh, now this one is saying find all zeros. So it's giving us the function. We're back to giving us the function given that 1 minus I is a 0. Right, we better look at one like this. Okay. All right, so if I'm trying to find my zeros, but I'm given one of them, I can just start right there. I don't need to do my P's and Q's yet because I know what one of them is, right? I don't want to try some that just might be if I have one that I know is a 0. So there's not any missing terms. So 1, -7, 18, -22, 12, and then 1 minus I. Okay, bring the 1 down. So that's still 1 minus I. Okay, and remember we did these last time. So you only add the real parts and the imaginary parts, and this imaginary part is 0. So -7 plus 1, so that's -6 minus I. So I might have to go over here to the side and see what is 1 minus I times -6 minus I. Okay, it's -6 minus I plus 6I plus I squared. But remember, every I squared is -1. So this is -6 minus 1, -7 plus 5I. Okay, so that's going to go up here. I didn't really leave myself enough room for this kind of problem, did I? 18 minus 7 is 11 plus 5I. So let's see what's 1 minus I times 11 plus 5I. Okay, 11 plus 5I minus 11I minus 5I squared. Don't forget, I squared is really -1. Okay, so this is 11 plus 5, 16 minus 6I. Goes right here now, 16 minus 6I. So when I bring this down, let's see, what's that? -6 minus 6I. Well, let's see what 1 minus I times -6 minus 6I is. -6. Okay, minus 6I plus 6I plus 6I squared. But I squared is what? Yep. Okay, so look, we got a minus 6I plus 6I. So -6 minus 6 minus 12. Woohoo! Okay. So we didn't know that was a 0, right? So the reason that we did that was to get, I don't want to erase everything, but I need to erase a bunch of this stuff. Okay. Now, since this was x to the 4th, right, this is x cubed. Okay, and I'm going to write it like this just so that there's no confusion. x squared plus 11 plus 5i x plus negative 6 minus 6i, right? So I really didn't need to rewrite this because I know I can't factor it with these complex numbers in here. But the reason that we did this division was to work this down to a cubic now. All right? And if 1 minus I is a 0, so is 1 plus I. So now I can divide by 1 plus I, and I'll be worked down to a square. So let's see how that works. So it's this exact same thing, it's just these complex solutions, complex zeros, you know, really add a bit of basic math. All right, so 1, give myself plenty of room this time. And we'll do 1 plus I. So bring the 1 down, okay, 1 plus I. Okay, so now I actually have imaginary parts to add. So negative 6 plus 1 is negative 5, and that's 0. So this is negative 5 minus 5i. Oh, that's 0 again. 11 minus 5 is 6. So 6 plus 6i. Oh, 0, 0. Yay! And look what I'm left with. X squared minus 5x plus 6, which we can now factor. Leading coefficient is 1, so I get a shortcut. This is, what is that, x minus 3, x minus 2? Okay, so I know my other two zeros. Here's one of them, and then here's another one, and here's another one. So, and don't forget we have 1 minus I also that was given. There's our 4 zeros. Okay, just takes practice. Yay, so let me know if you need anything. I'll see you next time.